Hello and welcome back. We are now going to do a problem that involves mixing two strong acids or two strong bases. Either way, same process. However, it is not one of each. Two strong acids or two strong bases. Here we have nitric acid reacting with hydrochloric acid. And we're going to figure out the concentrations of the nitric acid, hydrochloric acid, hydrogen ion, chloride ion, nitrate ion, hydroxide ion, and the pH and the pOH, and we're going to figure out if the solution is acidic, basic, or neutral. Oh my gosh. And this is happening when 50 milliliters of 0.20 molarity hydrochloric acid is mixed with 150 milliliters of 0.600 molarity nitric acid. Wow. Let's just start with our first step. Let's take this one step at a time. First, always identify the major species. So that'll be we have two strong acids here. We have hydrochloric acid and HNO3. It's not just one or the other, it's both. So we better put both of those up here at the top. HCl and, actually I don't want to use an arrow, HCl and HNO3. And let's identify what these are. They're both acids. And are they strong or weak? I hope that you said strong. If you didn't, it's okay. I still believe in you. Just learn those, memorize them. All right, step 2. What do we do next? By now, you should see the pattern that the second step is always write out the reaction. So in this case, since we have two major species, we're going to have two equations or two reactions. So our hydrochloric acid is going to react. Now this is a strong acid. Do I use a two-sided arrow or a one-sided arrow? Hydrochloric acid completely dissociates in water, so we'll use a one-sided arrow. Once it dissociates, it doesn't go back. Okay, then we also have HNO3, also strong, so one-sided arrow, NO3 minus. I hope you like the dinosaur colors that I picked for you. People were saying the color choices I was using were boring. So make sure that you know to use a one-sided arrow, and take note that these both have hydrogen ions, and so they are both going to contribute to our concentration of hydrogen ions that we find at the end of the problem. Okay, so step 3, we usually write out the equilibrium expression. But in order to write out an equilibrium expression, it must actually go to equilibrium. I only see a one-sided arrow here. It doesn't go back and forth. So there is no equilibrium expression. None. Does not go to equilibrium. Neither of them do. Now some of you are asking, I'm sure, well, what if one of them does and one of them doesn't? Well, then that's where this equation is going to split in two, if that's the case, and in one of them, if it does go to equilibrium, you'll have to set up an ice chart, and then what that doesn't would go down the path that we're about to go down now. So, step 4. It doesn't go to equilibrium. Well, in that case, we want to figure out the concentrations of everything. However, I don't know the molarities of everything once they've been mixed together. They have been diluted by being mixed together. So first we need to do the dilution. Now, let's see what our starting values are. Well, I'll write my equation first, I guess. M1V1 is equal to M2V2. All right, so let's see, I'll use another color. What's a good color? Pink seems like a dinosaur-y color too. HCl, we'll do that one first. Okay, so I don't know why pink seems like a dinosaur-y color. I just think it does. So its starting molarity is 0.20 from the top there, 0.20 molarity, and its initial volume is 50 milliliters. We are trying to figure out what its concentration is at the end. If this was weak, we'd be trying to figure out the concentrations at equilibrium. But here, there is no equilibrium. We're just trying to figure out the concentrations at the end after they've been diluted. So M2, now our final concentration. I want you to think to yourself, is it 150 or is it 200? It is mixed with 150 milliliters of nitric acid. That would make it 200 milliliters. So if you're trying to annotate this, lots of nice annotations, you probably would want to put a note on here. It's 150 plus 50 because it's diluted with. If it was diluted to 150 milliliters, then that means the final volume would have been 150. All right, so our M2 is going to be equal to, let's see, that should be 0.050 molarity hydrochloric acid, which tells us how much hydrogen ions and chloride. So let's go ahead and box this. This is something that it wanted. What was our final concentration that we had? It was that before it reacted. Now, our hydrogens, in this situation, we will have 0.050 molarity of hydrogen ions released. It's 1 to 1. If you look up here, it's 1 hydrogen for every hydrochloric acid. I'm not going to box that though, because I still have to figure out how many hydrogens are coming from our nitric acid. However, chloride ions, they don't come from nitric acid, so I'll box that one. I know I have 0.050 molarity chloride. There it is. That's been boxed. Okay, so now let's do the same thing except for nitric acid. So let's get our other color. You might see my ghost mouse moving around. That's because I'm switching colors on an invisible window. Okay, so get back to green. Okay, so now we have, again, M1V1 equals M2V2. Our initial concentration of nitric acid is 0.600. And you know, if you want to do this part on your own and figure out the concentrations of the nitric acid, the hydrogen ions, and the nitrate ions, then go ahead. You have all the tools you need to pause and try that on your own right now. All right, so for those of you who paused and are back, and those of you who are cheaters and you did not pause, I'm looking at you. There's my initial concentration, and my initial volume for this one is 150 milliliters. I don't know my final concentration, and my final volume for this one, it's diluted with the 50 milliliters of hydrochloric acid, so there's that. So my M2 is equal to 0.45 molarity HNO3. That's another thing we were solving for, so I'll box that. Now I'm going to split this off into my hydrogen and my nitrates. This is also 1 to 1, so I have 0.45 molarity hydrogen. Not boxing it yet because I still have hydrogens over here at the bottom. And then I have 0.45 molarity NO3 minus. Great, so I'll box that. Okay, so let's move on to our next step. Because we have 2 strong acids, or 2 strong bases, this one's acids, I need to now add the hydrogen concentrations together. So I'm going to take, here, I'll draw an arrow. This number is going to come up here. This number is going to go down here. So we'll end up with 0.050 molarity plus 0.45 molarity. So the concentration of hydrogen ions is equal to 0. Let's see, what does that become? 4, 5, 50? Yeah, 0.50 molarity. I'll box that. That's something I wanted. Awesome. So I've got all these concentrations that I asked for, but now I need to figure out the pH and the pOH. So step 6 is solve pH and pOH. So we know that the pH is equal to the negative log of the concentration of the hydrogen ions. By the way, you could do this without me by now. You've done this lots of ways, or lots of times. So I'll plug in my 0.0 or 0.50 molarity. Okay, so the pH, sorry if you can hear those sirens, it's really noisy out there today. 0.30, wow. Okay, so box that. Wow, that's a really low number. Okay, and then my pOH, I'm going to have to scroll down a little bit. pOH, I'm going to, there are two ways you could solve for OH. You could either subtract this number from 14, or you could, actually, you know what? Sorry, I'm thinking ahead. Let's solve for our pOH first. So ignore what I just said. pH plus pOH is equal to 14. So my pOH must be equal to 13.70. Excellent. Okay, so I'm not actually done yet. This problem asked me to figure out the concentration of hydroxide ions as well. So let's just do something like this. Okay, so to figure out the concentration of my hydroxide ions, you have more than one way to do it. You could solve for it out of this equation. So you could do, I'll write both of them. Oops, oh, I'm sorry, I keep punching the mic. Method 1 would be to do pOH is equal to the negative log of 13.70. So I'll move that negative over first. And I'll do, okay, this is log base 10, so that means I need to do 10 to the 10 to the, so this becomes 10 to the pOH is, I feel like I'm rapping, is 13.70. And I know that pOH is, what's my pOH? 13.70, so this, it's 10 to the 13.70. So you might have just heard Sonic the cat meow at me. Oh no, I'm dumb. I'm sorry guys, this is what happens when you zone out. Let's back up. I'm not going to redo this whole video for this. This will just be a lesson to you to not make mistakes like me. Okay, let me just erase some of this. Whoa, that's purple. While you're waiting for me to erase stuff, maybe you can you can figure out what's wrong with what I just did. Okay. Okay, let's try that again. I'm just going to start over. There. Okay. Trying again. You learn from your mistakes, right? That's how it works. Okay, so we know pOH is equal to the negative log of the concentration of hydroxide, which is what we are looking for. Oops. So I'm going to plug in 13.70 is equal to the negative log of my concentration of hydroxide ions. I'm going to switch the negative over to that side. I want to get rid of the log, so I'm going to use that base 10 to get rid of it. That's what happens. So let's do that. Hold on. There. This goes away. So I end up with 10 to the negative 13.70 is equal to the concentration of hydroxide ions. Whew. And our concentration of hydroxide is equal to 2.0 times 10 to the negative 14th molarity. Oh my gosh. Okay. Sorry about that. The other way you could solve for this would be to say, well, I know that the concentration of my hydrogen ions times the concentration of my hydroxide ions is always equal to what? 1.0 times 10 to the negative 14th. And I know the concentration of my hydrogen ions. It's 0.50 from up here. So 0.50 times the concentration of my hydroxide ions. So if I divide both sides by 0.50, I end up with, oh, look at that, it's the same number. It doesn't matter which one you choose. They both work. You have options in this unit. Isn't that nice? All right, well, there you go. That's how you solve this problem. See you next time.